So if you have a 0 in the first column of any one of the rows, but the remaining that you have non-zero elements in the remaining columns in that row, you apply this remedy. Okay, you put an epsilon instead of 0, and you continue with normally with the test. But if you have 0 in the first column, and the remaining columns are 0 as well, we call that all 0 row. Then replacing 0 with epsilon greater than 0 doesn't work for those cases. Does not work. In that case, you apply the second remedy, which is explained here. So let's show that on this example. So this is what I'm talking about. This is an all 0 row, right? Okay, so in that case, what you do is the following. So instead of putting epsilons here, you go back to the previous last non-zero row, and then you construct a polynomial from there. Şurada bir yanlışlık var bu arada, ona dikkat etmek lazım. So this is a fifth order polynomial. So the first row is the fifth power row. This is the fourth power, third power, second power. So the polynomial here is the following. There should be 4 times s to the power 2 plus 4. So there shouldn't be 4 here, so that's a mistake. This should be 2. Okay, so you construct that polynomial from the last non-zero row. Then you differentiate this polynomial, and the taking derivative of that with respect to s gives you 8s. And instead of the 0 row, you use this polynomial. So you put s 8 for that 0. Just like how you initially start the array. So you assume that this was your polynomial and you form the array using this part. So this is the first order polynomial. You write 8 and there's no other term to write here. And then you complete the test using that, and then you use the resulting array to conclude stability. Doğru. Yani şöyle bir şey oluşturalım. So let's just make up some numbers. Suppose that we have an 8 order system and the coefficient of 1, 3, 5, 6. Daha gitmesi gerekiyor mu? And there should be a constant number. O da 1 olsun. Şimdi tabi burada olmadı ama atıyorum burada mesela 0 kalmış olsaydı, obviously that's not what we're going to get, but just suppose for the moment that we had an all zero row here. Then we would go back to the previous row, and the polynomial here is 2 times s to the power 7 plus 4 times s to the power 5 plus 3 times s to the power 3 plus 1, and taking the derivative of that gives 14 s. Doğru. 20 s to the power 4 plus 9s squared plus 1. So instead of this zero row, we would use these numbers here. Okay, so you complete the array without any divide by zero errors. So let's come back to this example. Şimdi ne oldu? So this was our array. And then we have replaced the zero with this part. Okay, so this is the array after the that modification. So normally we check the first column, right? And we see that there are no sign changes after this modification. If this is what we obtained initially, then we would say that this is a stable system. But since we obtained this result after applying this modification, then we cannot conclude that the system is stable. In fact, the conclusions are explained here. So after the modification, we complete the test and get a non-zero first column with no sign changes. But there was an all zero row in the test. And all zero row in Routh array occurs in one of these three cases. So again, having an all zero row happens in one of three cases. The first one of these three cases is the case where we have a pair of equal roots with opposite signs. That means having real poles that are symmetric with respect to the imaginary axis. So if you have a pole at minus a, then there's another pole at plus a. And if you have a system like that, that system gives you a row of all zeros. And if there is a situation, this is the case, we get one sign change in the first column. Okay? But in this last example, there is no sign change, right? So apparently this is not the reason why we had an all zero row. So let's take a look at the second possibility. The second possibility is the following. The second case is there's one or more pairs of purely imaginary poles, which means poles symmetric with respect to the real axis with real part equal to 0. If this is the case, then there are no sign changes in the first column. So this is what we had really, right? Because in our example, after the modification, there was no sign changes in the first column. So according to this, we must have this situation, two purely imaginary poles. Bunu da yazayım buraya. This is what we have in the above example. But let's take a look at the last case. And the last case says that it's basically a combination of the first two cases. In the first case, we had poles symmetric with respect to the imaginary axis. In the second one, we had poles symmetric to the with respect to the real axis with zero real part. The combination of the two gives the following: we have a double pole and the symmetric of that double pole with respect to the imaginary axis. And if this is the case, there should be two sign changes in the first column. Okay, so if you get if I give you a polynomial and that polynomial in the Routh array gives you a zero row of all zero elements, then you need to apply this modification, and after the modification your conclusion should be based on these three cases. Okay, so you complete the array, you check the first column. If you see one sign change, then you can say that this is what I must have. If you have two sign changes, then the last case is your system should be satisfying this condition. And if you get no sign changes, which is what we had in this example, then the system should be satisfying this condition, which means there are two purely imaginary poles. In fact, if we just check the poles, we should see that. Let me do that for you. So that was the polynomial. So let me tell you the roots of that polynomial. 7 and 4. And these are the two purely imaginary poles. Okay. So this test is really simple, and if normally in the previous years I didn't give the rule for that test in the exam, so I expected the students to know this. That's simply because I don't know how to give a hint for that. I have to write the entire test in the exam paper, and since normally I don't have that much space, I don't give this information. And this is an easy test, so I don't think it will be a problem for you to remember this formula, right? So this is the formula you need to remember. You just need to remember this relation, and remembering that relation will be. Ya da şöyle yaparım, sınavda şu formülü veririm, bunun A'ların B'lerin ne olduğunu siz hatırlarsınız, o kadar öyle bir şey yapabilirim belki. Okay, so this is everything there is to know about this test. And as I said several times already, this test only gives you how many unstable poles your system has and nothing else. It doesn't give you how fast your system converges or diverges, or if there will be any oscillations or not. You don't get any of that from this test. Okay? Yeah, bir şey demeyeceksin. So if you, okay, so in that case you can conclude that your system has two purely imaginary poles. Then according to the previous definitions, that means that your system is marginally stable. So I think there's another example here. Let's take a look at this example. Bu da güzel bir örnek. Arman, bu sana teneffüste göstermeye çalıştığım şeyin örneği varmış zaten burada. So let's take a look at this example. So this is a polynomial given. So the first coefficient is positive, that's fine. And then there are some negative coefficients. In fact, there are 3 of them. Okay? So without even applying the test, you can tell that the system is unstable. But if you are asked the number of unstable poles, so you may get a so there may be a confusion here that since there are 3 negative coefficients, there must be 3 unstable poles. But there's not really a rule like that. So to find out the number of unstable poles, you need to apply the test. And once you do that, you get this array. And if you check the array, there's just one sign change. You start with positive, all numbers are positive. It switches to negative, but the last element is negative as well. So there's just one sign change, which means there must be one negative or unstable pole. And if you calculate the exact pole locations, you see that there is indeed one unstable pole. Okay, so having 3 negative coefficients doesn't mean that there should be 3 unstable poles. Okay, so this is a good example for that. Burada sanki haddinden fazla örnek olmuş ama fazla örnek elde zarar vermez. Okay, in this case, again, a fourth order system. All the coefficients are positive, so we cannot say it's unstable. We need to use the test. When we do that, we get an all zero row. We apply the second modification, construct this polynomial using these two, take the derivative, and we get a 12 here. So we replace the 0 with 12. And then the last element turns out to be 6. So no sign changes at all. That means there must be a pair of purely imaginary poles. And if you calculate the pole locations, that is indeed what you get. Okay, so these are the purely imaginary poles. And the other poles are stable. Okay? Okay, so I'm going to skip this part, the transient characteristics. So you will need to study this for the lab report. So to answer the questions related to things like settling time and rise time, you need to check this. They are just very simple definitions. There's really nothing interesting here. Okay, so there is one very good example of using this test, and I would like to show you that example. As I said before the lecture, the example is not very straightforward. It's very hard to see that, but I'm going to explain step by step what I do here, and hopefully that will make some sense. Okay, so this is where I'm going to start the problem. So suppose that I have a missile. In fact, this is the missile roll dynamics, and we are given the system is given in that form. So the input is the aileron deflection angle. So we use ailerons to control the roll motion. You know that. So there's a first order transfer function, and that transfer function gives you the roll rate. This is roll rate. And so this is how fast the missile rolls, right? And if you take the integral of that, the result gives you the roll position. So this is the roll angle. And remember that the integral action has the Laplace transform of 1 over s. Okay, so I have these two blocks that these two blocks together form the roll dynamics of a missile. So if you give an aileron deflection, that passes through this first transfer function gives you the roll rate, and if you pass the roll rate through the second block, the result gives you the roll angle. Okay? And we should use some numbers. So the first block transfer function is given as 3000 divided by s plus 1. So this is the dynamics of the missile. So first let's concentrate on this part. Suppose that I apply a step input to the ailerons. And forget about this second part. What I get as the roll rate, we can now predict that, right? So this is a first order system. We have one real pole at -1. So this is a stable system, right? Since it is on the left hand side. Since it's a real pole, the response should be an exponential. There should be no oscillations since there's no imaginary part. And the time constant for that is 1 second, right? So if I apply a unit step input, which means this delta aileron, or the Laplace transform of that should be 1 over s. Starting from 0 initial conditions, the roll rate will converge to some constant number, right? We are comes with 0 initial conditions. Stable, the response converges to a constant number. O converge ettiği yeri nasıl bulabiliriz? Bunu söyleyebilir mi birisi? Kesinlikle. Bunu herkes görebildi değil mi? Okay, so converge the constant number and the value the response converges to can be found by using the final value theorem. So the steady state value, let me call that PSS, is given by S times S times G of S, which is 3000 divided by S plus 1, times the input, which is 1 over S. So the result is 3000, right? And this 1 over S is used here. And we can also find out how fast it converges there, right? Burası saat 7 oluyordu galiba, değil mi? 0.67 times PSS This is PSS. So this should be one time constant, but the time constant was 1 second. So it should be 1 second here, 2 seconds, 3 seconds, 4 seconds. Okay? Good. Now, the response for the P variable, which is the roll rate, is given by that curve. And if you want to find out how this value changes the roll angle, the roll angle is the integral of roll rate. The roll rate we just found out, and the roll angle is the integral of this, but this converts to a constant number, and if you keep integrating a constant number, you get something that grows continuously, right? So if you so that's basically the integral of this. So for example, the value at 3 seconds, again, assuming we start from 0 initial condition, the roll angle at 3 seconds should be the area under here. The value at 4 seconds is this. The value at 5 seconds is that. So you keep integrating the curve. That means the area keeps growing and growing, and then you get something like this. It keeps increasing forever. Okay, so that's the roll angle. In fact, I have this in simulation, so let me just run this file. So this is what you get, the roll rate and roll angle. Now, so we haven't used the Routh test so far. Okay, so in the second part, we are to design a controller for this system. So we didn't use the Routh test for the above. In the second part of the question, we use the following feedback controller. That means instead of applying an open loop input to the ailerons, we apply the aileron deflection according to the above equation. So this is the equation used for the controller. So let me just draw the block diagram again. So I have delta, and then I have this transfer function. The output of that is P, and then there's another block with transfer function 1 over S, and the result of that is the roll angle. So and this delta is calculated according to that equation. So that means there is this term minus this term. Okay, so let me just put a summation junction here. So the second term is subtracted. The second term is P times Kp. So P is here. I get that P from there. Multiplied with Kp and subtracted here. Okay, so this negative side is due to that negative side. Then I should be adding this into that summation junction. Kp times phi desired minus phi. So I have bunun ikisi Kp olamaz ya. So let me make this Kd. Otherwise it doesn't make sense to use the same number twice. So I make that Kd. So this is Kp. And the Kp multiplies this difference. Phi d minus phi. So the phi desired is there. And I should subtract phi, but phi is the output of this second block. Okay, so what I did here is I drew the block diagram for the closed-loop system using the controller equation. Okay? We obtain this block diagram using the given controller equation. So I have these two parameters in controller, Kp and Kd. So these are two numbers that I can choose as the controls engineer. Okay? So I don't know how to choose them yet. There's no reason. The question just tells you that use this controller. So it is given in the question that you should be using this controller. So this is just one controller design. So obviously you can use many different designs. Instead of using constant numbers here, you can use transfer functions. So they will all be different controllers. But in the question, you are given the structure of the controller. You are only asked to find these numbers. Okay? Okay, so for the given controller structure, this is the block diagram. Nerede yazayım olmadı? In the question, we are controller structure, the controller equation, and we will need to choose the two design parameters, and these parameters are those two numbers, Kp and Kd. To be able to choose them, let us first find the closed loop for the above system. So I'm going to reduce this block diagram, and then I'm going to find a single transfer function from this input to that output. So you know how to do that. So I can just copy the result from here. Yani nasıl yapılacağı burada da anlatılıyor zaten herhalde. Şimdi yani burada kontrol tasarım ile ilgili aslında çok güzel bir örnek. Tabii örnek üzerinden gidiyoruz şu anda ama still it's a very good example for controller design. So when you calculate the closed loop transfer function, you get this quantity. So from here we see that the closed loop system is a second order system, which means there should be two poles for the closed loop system. And these two poles are determined by the coefficients of this polynomial, right? This polynomial. But if you see that for a second order system, there are two poles, and for two poles, the location of those two poles are determined by two scalar quantities. And in this closed transfer function, we have two free parameters, and these two free parameters are the ones for the controller, Kp and Kd. Okay? Let's see. So let me just repeat. For a second order system, the pole locations are determined by the coefficients here. And if you look at the coefficients, there are two of them. And I have two free parameters. That means these two coefficients can be set arbitrarily by using these two coefficients of the two parameters of the controller. So this is a very important statement. We can set the closed loop poles anywhere we want by using these two parameters. So if I use these polar coordinates for the second order system, I write it in this form using the natural frequency and the damping ratio. And I can solve for Kp and Kd to match any natural frequency and damping ratio I want for this system. Okay? So suppose that we want the closed loop system to have a certain natural frequency and a certain damping ratio, then if I set the Kp parameter and Kd parameter according to these two equations, then those numbers will make the closed loop poles of the system placed according to these two numbers. Okay? Okay, so first let me tell you that we still haven't used the Routh test. So we have just designed the controller for the given missile. So we were given the controller structure. Normally the controls engineer has to decide on the structure himself. But since we don't have any experience in that yet, I gave you that use this controller structure. This is the controller you need to use. After forming the closed loop system, it turns out that if I choose the Kp and Kd parameters using these two equations, then the natural frequency and damping ratio of the system will be given by these numbers. And I pick these numbers first on the regime. In this example, it turns out that poles of the system we first choose acceptable pole locations and find homogeneous zeta corresponding to those locations. Then the Kp and Kd values given by above equations guarantee that the closed loop poles have the omega n and zeta values we picked. Okay. So again, the Routh-Hurwitz test hasn't been used yet, so I'm going to show that tomorrow. So our time is over now, so let me stop here and I will continue with this example tomorrow. Arkadaşlar, dalmadan önce bilmiyorum, yani çok bir şekilde takip edemediğinizi gördüm.